the pace upon which I've read this, maybe my headspace is in a different place, but the pace upon which I read this just was like 25% slower than I read software architecture. And maybe that's because I was head nodding a lot of the times, where here I was like, oh, maybe that's why my approach is incorrect, or oh, that's why we do it this way, right? There's a lot of these like aha moments that I kept running into.
Hey everyone, welcome to Book Overflow. This is the podcast for software engineers by software engineers, where every week we read one of the best technical books in the world in an effort to improve our craft. I am Carter Morgan, and I'm joined here, as always, by my co-host, Nathan Toups. How's it going, Nathan?
It's going great. Hey, everybody.
Well, we are excited to be here, excited for the episode we have prepared for you today. Just as always, make sure to like, comment, subscribe, especially if you're on YouTube. If you're on any of the podcast players, make sure to give us a follow. And leave a 5-star review. We always like seeing those 5-star reviews trickle in, and we've got quite a couple now. And we're excited about our follower count growing. By the time you hear this, we'll probably be about 2,000 on YouTube, and then we're at about another 1,500 across audio platforms. We have to extrapolate a little there because we only know how much Spotify gives us, but we know about 1/5 of our audience is on Spotify, and 300 of you are following us there. So I feel pretty confident in that math. And just as usual, make sure to share the podcast. This is something that really thrives when people share it, when it gets a vote of confidence. And I think it's something that we hope that it's easy to share with your coworkers, and that you feel confident recommending what we think is substantial, good technical content. We also have another interview live. This one is with Devin Davies. Now, this is a little different from our usual fare. Obviously, and it's called Book Overflow. We tend to be pretty focused on the books, but we had the opportunity to interview Devin Davies. He is an Apple Design Award winner. His recipe app Crouton just won the Apple Design Award. And if you listen to the interview, it beat out some prominent apps like Arc Browser. And just kind of as it happened, we got the chance to talk to him. He wanted to come onto the podcast. And so we didn't want to turn him down because he seems like a fascinating person. So we did an interview style that focused a little more on his learning strategies and how he taught himself to create this award-winning app just on nights and weekends, which you'll find out if you listen to the interview. A little different from our usual fare. And Nathan, how'd you like that interview?
It was great. I love seeing folks discuss the creative process and his personal journey, and how he goes about problem solving. It was really cool to see that he was solving a problem for himself that resonated with the public, and then eventually got to something that he wanted to run with. And so, yeah, I'm kind of glad that we stepped out a little bit. I would love to get feedback from the audience. I want to see what y'all think. You want more content like this, because we really enjoyed it. I think it complements the sort of professional journey and professional growth theme of the show. And so give us feedback.
Yeah, obviously, our pledge to you is our weekly Monday episodes. Those are always going to be book focused, discussion focused, and that we can control. We do get the chance to interview folks. Again, it's been mostly authors up until this point, but we have interviewed some non-authors like Devin. Like Nathan says, we thought it was in keeping with the theme of the podcast, just kind of continuous education, self-study, improvement. But let us know if you feel it's a little outside the wheelhouse, if it's not what you're tuning into Book Overflow for. We'd love to know. We still might keep doing them because it was really, really cool talking to Devin. But we always want to hear from the audience. And then just as another bit of an announcement, we are going to be adjusting our reading pace just a tiny bit, just to give you behind the scenes. I know we say that we do a new software engineering book each week, but obviously you've seen we have a lot of 2-parter episodes. That's because what our rough commitment has been is to read about 200 pages a week. We are discovering for ourselves that 200 pages is about the upper bound of what we can handle each week. And it actually happened with this book. This book is about 260 pages minus the index. We thought we could get it all done in 1 week, and we realized we just would not be able to do this book justice by covering it in 1 week. So we're adjusting the reading pace just slightly to consider 200 pages an upper bound. And so we have a book like this that's 260. Instead of trying to cram it all in 1 week, we're going to split into 2 weeks. So we have some 1-parter episodes planned in the future that became 2-parters, and we have 1 2-parter that became a 3-parter. We feel confident in this, not only because, one, we're playing the long game with this podcast, and avoiding burnout is key there. But also too, because in every single episode we've done, we have always skipped material. There's never been an episode where we feel like we cover everything in the book. So we feel confident that even if we read at a slightly slower pace, we'll still be able to deliver some high quality, in-depth technical discussion. So again, you can let us know in the comments. You can email us at contact@bookoverflow.io if that's a change you're not happy with, or if a change you are happy with, let us know, because we also like the positive feedback. Lets us know that we're doing right by the audience. Any thoughts on that, Nathan?
Yeah, I mean, I think it stays on theme, and obviously, I think the long game is this is a book discussion club as a podcast, right? And I think some page count is a really good threshold. We're figuring out what that means, but I think the other part is, and we haven't figured out a way to measure this yet. Some books have a density ratio that's in there as
Very
well.
true.
We loved the Wolfram ChatGPT book, which was actually relatively short, but it took a lot of careful reading. I had to go back and reread certain sections. And so, to be able to approach this conversation with an intelligent perspective and making sure that I have a thoughtful take, we're figuring out what that wiggle room is. And so, yeah, we'd love your feedback. Are we blasting through material too quickly that you'd like us to dive into, or are we getting too granular, right? Like that's the dance that we're on as well, like figuring out the right thing. I will also say, Carter, I don't want to put you on the spot. I know that the fall semester is coming up soon. Have you scheduled classes for the fall?
I have scheduled classes for the fall,
And
and
are
I
you
did not get
taking? Okay.
graduate algorithms. I did not get into it. It was
Okay.
it's a madhouse. So
Okay.
yes, for anyone listening, you know that Nathan Toups and I, how we met each other was through the Georgia Tech online master's program. Nathan, and I envy him, has graduated. I am close, but not quite there yet. There is a class in the program called Graduate Algorithms, pretty universally regarded as one of, if not the hardest classes in the program, and everyone delays taking it until like their final semester. So
right,
I'm approaching that. I've got to take it. Not looking
yep.
forward to it.
Because everybody delays, therefore you must be delayed typically. So I
Yes.
didn't get to take it till the end, but I also have a lot of empathy. It is more important for Carter to do awesome in that class than it is for us to read 200 pages a week. So that is
Yeah.
my concern as well.
Like I said, with this podcast, we're going to be doing this for a good long while, we hope. We've talked, Nathan and I, and said that we would rather cut down to an episode every 2 weeks than get burnt out and not do it entirely. We don't think that's going to happen.
Mm-mm.
Again, we might adjust the reading schedule down. We're not sure. Well, here's our promise to you. We will be very communicative throughout this whole process. We're very, very excited about how this podcast is going. It's funny in some ways, just because we have had a lot of good success starting out and been able to interview a lot of cool people like Uncle Bob and Brian Kernahan and John Osterhout and Michael Feathers and all the other authors, right?
Yeah, Neil Ford, a bunch of great
Neil
people.
Ford,
Yeah.
Mark Richards. It feels like we've been doing this for a while, but we actually haven't. I think like we just barely hit 2 months of podcasting.
That's bananas.
Yeah, so like we always say, we're at the very, very early stage of this podcast, but we are very confident in it. We're confident that it'll continue to grow, and we have no plans of stopping. I know that's a little more housekeeping than we usually do. Hopefully you're still tuning in. But we are excited about.
I put chapter markers in the episode. So if you're watching this on YouTube, feel free to hop around. So that's why it's there.
Absolutely. Okay. Well, we are excited about the episode we've got for you today. So this week we're doing Building Evolutionary Architectures and we have quite a few authors this week: Neil Ford, Rebecca Parsons, Patrick Kwa, and Pramod Sadalage. This is in keeping with my habit of probably butchering these people's names. Let's do a quick author introduction for each of those people. And that's we've got Neil Ford, who we have read Fundamentals of Software Architecture by him and interviewed him. But in case you forgot, he's the director, software architect, and meme wrangler at ThoughtWorks, a global IT consultancy with a focus on end-to-end software development and delivery. Rebecca Parsons is the chief technology officer emerita at ThoughtWorks, having previously been the CTO since 2007. Patrick Kwa is a seasoned technology leader with 20 plus years of experience, having done a wide variety of roles, including being a developer, tech lead consultant, CTO, and more. His current mission is accelerating the growth of technical leaders through coaching, mentoring, and training. And Pramod Sadalage is a principal consultant at ThoughtWorks, where he enjoys the rare role of bridging the divide between database professionals and application developers. So we've got quite a murderer's row here of software professionals. You can tell in the book that it's a very dense book, and you can tell that all of their experience really shines through and informed all the different chapters. For the book introduction, this is what we get off the Amazon blurb. The software development ecosystem is constantly changing, providing a constant stream of new tools, frameworks, techniques, and paradigms. Over the past few years, incremental developments and core engineering practices for software development have created the foundations for rethinking how architecture changes over time, along with ways to protect the important architectural characteristics as it evolves. This practical guide ties those parts together with a new way to think about architecture and time. So, like we said, pretty dense book. We're really enjoying it so far. And we always have to give our general thoughts on the book. So, Nathan, why don't you give us your general thoughts on what you've read so far?
Yeah, so you'll get a lot of clues of what the book's about just from the title. um, it dives deep into philosophy and tactics that help you guide the evolution of a system, and that guided evolution is like a big theme in this book. Um, I think it's a wonderful complement to fundamentals of software architecture. I would say in a lot of ways it's a prerequisite because they get to dive into the general topics of architecture, and this book expands on it and says, "Hey, this is going to change over time. It's either going to change because you did it on purpose, or it's going to change because the world changes." And you really need to have a strategy for this, which I really appreciated. And I'll say this book is rich with information, but it's very dense. The pace upon which I've read this, maybe my head space is in a different place, but the pace upon which I read this just was like 25% slower than I read software architecture. And maybe that's because I was head nodding a lot of the times, where here I was like, oh, maybe that's why my approach is incorrect, or oh, that's why we do it this way, right? There's a lot of these like aha moments that I kept running into.
Yeah, this book was the catalyst for us saying, "Hey, maybe we need to slow down the reading pace just a bit," because, like Nathan said, and there's not really a way to measure this until you actually get into the book. It's dense. Um, and I was definitely kind of, before we decided to slow down the reading pace, I was just blazing through it, and there's definitely a part or two where I'm like, well, I hope Nathan understood that part better, because I didn't, and I just got to keep going. And so when we decided to slow down the reading pace, it was good to revisit some of those parts. Yeah, I agree. It's very much a companion of Fundamentals of Software Architecture. It explicitly references Fundamentals of Software Architecture at several points. We'll talk about this in kind of our who we would recommend this book to section. I think I would recommend Fundamentals before this one. But that's because, like Nathan said, Fundamentals is a bit of a prerequisite to reading this. You can read this without reading Fundamentals, but I think the two they complement each other very much, just like Nathan said. Where it differs from Fundamentals a little is that it almost focuses more on the theory of building architecture than any particular architecture. Fundamentals covered a lot of that too, but Fundamentals, the whole second section is devoted to the various kinds of architectures. Whereas this takes a bit more of an architecturally agnostic point of view, and instead talks about, assuming you've chosen any given architecture, how can you build it in such a way where it continues to evolve as requirements change? And yeah, I mean, this book, it does exactly what it'll tell you to. It's going to teach you how to build evolutionary architecture. And we're going to talk a bit about what that means, evolutionary architecture, and kind of why this book exists in just a little bit after this break. And we are back. Now, if you're tuning in and you've heard of this book, you might think, okay, building evolutionary architecture, what does that mean? What does it mean for architecture to evolve? Basically, so let's set the stage a bit, right? Which is in the 90s, right? And kind of before, if you want to build a software system, and we talked about this when we read Fundamentals of Software Architecture, right? And kind of those old architecture styles. What are some of the main challenges with building software? Well, a huge challenge that we don't have is licensing, software licensing, like the operating system licensing for the different computers. Just the computing power was all very, very, very expensive. And we've switched to a model today where, thanks to cloud technology, individual computing units aren't nearly as expensive as they used to be. You can spin them up and spin them down very easily. And most everyone uses like Linux as their for their servers, and so the operating systems have all become open source and they're much less expensive. So it kind of frees you up to build more flexible software architectures. Because in the past, you would really want to build the minimum possible thing you could to conserve cost, and once you built it like that, you kind of wanted to lock it in. So that is the old view of architecture, which is this is something kind of classic waterfall style. You define up front, you lock it in, and then you want to have that design be as perfect as it possibly can, because once it's locked in, it's locked in. Not so anymore. We don't necessarily have to lock in the architecture style today, and the web is a lot more dynamic than it used to be back in the day. So that's kind of the idea of this book is, how do you build a software architecture that can evolve and can evolve to meet the challenges of your business as it grows, or even just as it changes. Nathan, what are your thoughts on this whole idea of a evolving software architecture?
Yeah, there's a quote kind of in the depths of the first or second chapter, and there's also a quote from the preface that I liked a lot. In the preface, it said, "Systems must evolve to meet new demands of their users and to reflect changes in the constantly shifting software development ecosystem." And in the first chapter, they even also have a section that's called "Why No Microservices in the Year 2000." Right? They go on that. They elaborate on this exact same thing that Carter was bringing up. Is um, there's been some fundamental shifts in how we build systems, right? You used to have a co-location always, right? Now you can still co-locate, you can still put buy space in a data center or build your own data center, put your own servers in there. Or you can go to cloud computing and do the Netflix model where you can, scale up and scale down, or um, do all these wild things. But the machinery to make those changes and those design decisions didn't exist in the year 2000, right? Um, Everything was licensed software. Everything had a long cycle. And when we think of architect, they spend a good amount of time talking about how when they talk about architects and architecture, it's not like the blueprint architecture of a building, right? Where you really do need to have everything locked down, because any change is really important. I think later in the book, they even talk about this, that Neil Ford has a background as an engineer outside of software. And, when you were doing mechanical engineering or these other things, it was very expensive to have to retool, a piece of circuitry, a piece of hardware that was going to be manufactured and distributed. And so that design phase and making sure that you thought about every edge case was, really important early in the process. That's not possible now, right? The world has been eaten by software. We're in a constantly changing ecosystem and environment. And this is one of the advantages of software. We can change it. We can change it quickly if we build the system properly, right? And so instead of saying, "Hey, we're just terrible at planning in the software industry, and this is why software is changing all the time," this book kind of flips that whole idea on its head and says, um, "The world's changing all the time, and you need a system in place. You need to architect a system that can rapidly adapt to this change, right?" And it gets into this one quote that they had. It says, "There are no separate systems. The world is a continuum. Where to draw a boundary around a system depends on the purpose of the discussion." That's Danella Meadows. And again, this really, I think there's a lot of intuition. I think there's a lot of belief. And if you've seen DevOps and CI/CD and autonomous teams who are making, bold changes to a system within a very large company, you see these things at work, but you don't necessarily know, why does it work? Like, why is this better? And so I think especially this first chapter, does an amazing job of kind of like laying out their thesis statement of like why they're going to dive into these things.
This is slightly off topic, but you mentioned Neil Ford, how he was a real engineer, I guess. Do you have any strong preferences on? I know some people really don't like the term software engineer and prefer software developer. Do you have any strong preferences on what you call yourself, or software
I,
professionals using the engineering term?
I'm so back and forth, and I do think there's a difference, but I also think, you know, some of it are like aspirational titles that organizations put, right? To me, and I think I'm going to butcher it, but Russ Cox, who's the one of the core maintainers of Go, he's like led the Go project for years. He actually just stepped down. He said, and I'm going to butcher this, but it's that software engineering is programming over time, or something to that degree. Is that there's this time and change management element, that there's this professionalism of understanding that systems change and that we have to build this in this maintainable way. But I do think a lot of people are kind of developers. And if you think of a developer, like I think of like a real estate developer, which is like, hey, people want this kitchen and they want, 2-car garage and they want a yard that's this size and they want all these things. And so there's a lot of folks who use programming to kind of rapidly implement features or, kind of spit out a product. And I think software developer is a very good way of thinking about what you're doing. And it's not that one's better than the other. I think I would like a core library maintainer to be an engineer, right? Where I think a lot of folks are probably doing software development work, right? Where you're getting a form to, meet the needs of a funnel for a marketing team that puts it into a database that can be analyzed later, right? Something like this. You may not need the person who's like maintaining libc or something to make decisions on how to do that. I also loved it, and it's old school, but I actually love that some of the graybeards in the industry, right, the folks who've been around a while, they still call themselves programmers. And I feel like that's kind of an
Yeah.
antiquated term, but there's also sort of a badge of honor, or hacker, right? So not somebody who's doing something nefarious, but somebody who's doing something because they're deeply interested in it. I love the titles. I think that it actually, to me, when somebody refers to themselves a certain way, it kind of gives me a perspective on how they see themselves if they have control over that title. Obviously, if you walk into a company and they hire you as a software engineer, then that's your title.
Yeah, I used to teach the University of Central Florida coding boot camp. This was interest rates were lower, folks, and I I always told the students there that I preferred the term software engineer as opposed like programmer or coder or something like that, only because to me, when you get into kind of the nitty gritty of it, engineering is, I think, the best term of what you're doing when you're debugging something or building something or making choices and evaluating trade-offs. It is funny though, in my family, my grandpa is a chemical engineer, and then one of my uncles is a mechanical engineer, and one of my cousins, he's studying mechanical engineering too. And I was just talking to him about that. He's like, "Yeah, like Grandpa's so excited. We're gonna have the first engineer grandchild." He looks at me, he's like, "Sorry, they don't count you, Carter." And
Right.
I didn't tell this to him, but my response to anyone who says that is, I don't really care because I'm pretty sure I get paid 2 to 3 times as much as your garden variety mechanical engineer. So you can
Yeah,
call me whatever you
I don't
want.
think that
I
would
don't
have gone
care.
over so well at
Yeah,
the family dinner. Right.
exactly. Hopefully, none of them listen to this podcast. Yeah, so at the end of the day, I don't care what I get called. I just want to work on interesting problems and be paid well to do it. But to me, when I think about what we do, engineering sounds, I don't know, that term makes the most sense to me. But then again, I also think what we do is probably pretty similar to like what a plumber does. And I don't mean that like as a disrespect, but I think a plumber has to, troubleshoot why something's not working. When they're installing new systems, they have to figure out the best way to do it. But we don't call plumbers engineers either. So I don't know. Let us know what you think, listeners. Um, but yeah, so we talk about this idea of evolutionary architectures. And so we've been talking about now about kind of, okay, so you want your system to evolve. How do you know that it needs to evolve? How do you know that it might not be meeting the needs of your current user set? Um, Kind of the chief tool they give here is something called a fitness function. And we talked about fitness functions in the fundamentals of software architecture episode, but it's key here. So let's talk a bit about what a fitness function is. They define it. They say an architectural fitness function is any mechanism that provides an objective integrity assessment of some architectural characteristics. So they say that the objectivity is key here. So when we talk about architectural characteristics, what are we talking about? And again, we covered this in fundamentals, right? These would be things like latency, availability, scalability, security, kind of these overarching, I don't know, properties that govern a system. How would you describe this, Nathan?
Yeah. I thought a lot about this because fitness function, it is kind of a nebulous sounding term, but if you kind of flip the words around, do a little wordplay, you know, does the functioning of the system fit its need, right? Or is it acting in the way that we expect it to? And can I poke and prod at pieces of it? So a lot of this, your spidey sense might go off and say, okay, well, that means I need to do some monitoring or I need to use some unit tests or metrics. And the thing is that all of that is true. Like, so they talk about the different levels of scope of when you'll hop in, and that an architect's job is to think about fitness functions to test that a system's behaving the way that you expect it to, right? Um, and so what's kind of cool is that this gives you, they're a big advocate that architects are not somebody who sits in an ivory tower and dictates the way the system should function, that you should be writing code, that you should be getting your hands dirty. You should go hang out with the software engineers and really understand what kind of problems you're trying to solve. It also means that just because you run unit tests in the CI does not mean it's a fitness function, right? You need to have your sort of insights into how unit tests are functioning, making sure that it's actually testing the fitness of the application. And so they actually, in the book, they have this like Venn diagram, and they have like all these sections like monitoring, unit test metrics, chaos engineering, a bunch of other cool things that they talk about. And then there's a circle that kind of touches all of those. That's fitness functions. So it's this idea that it's interdisciplinary, that a subset of unit tests are actually fitness function tests, right? A subset of metrics are actually going to help you measure and make sure that you understand how the fitness of the system is in place. And again,
yeah. So
love
what
this
might
framing.
that? Yeah, and so what that might look in practice would be, for example, they talk about Java has this library called like ArchUnit, which is kind of like JUnit, the unit testing library, but for architectural characteristics. So you might be able to say things like all classes that depend on this class should not depend on this class, right? Because maybe you want to avoid tight coupling between two kind of classes. You can have monitoring, right? When I worked at I worked at a large cloud provider, and like this is all we did was it was fitness functions out the wazoo. But we would monitor kind of every conceivably useful metric for our service. Latency was a big one, right? We actually had a meeting every single week where we would review all of those metrics, and we would look and say latency spiked in the Oregon data center for about an hour this past week. Did we catch that? No. Okay, what's going on there, right? And then that's what would trigger our pages is when these metrics would breach a threshold. And so yeah, like all that was fitness functions, and then it kind of gets what I like about fitness functions, what they propose here, is that they should be automated, and that's something where Nathan says like that software architects should be writing code. They shouldn't be in ivory towers. And one way that they can get out of the ivory tower and actually write code is to be writing automated systems that enforce these fitness functions. I'm such a big believer that if there's not an actual mechanism, if there's not an actual system, some sort of automation that is enforcing a behavior you want on your team, like it's just not going to happen. And I don't mean that because like developers are lazy or because they lack discipline or anything like that. I just think we're busy. And I think one of the best things about us as software developers or engineers, I'm going to be so self-conscious the rest of this episode about what I call people now, is we love to build things and we love to just ship as much code as we possibly can. And in our love to build things, we will often cut corners. And so one way that a software architect can help their engineers not cut corners is by writing these kind of automated fitness functions. I was liking reading about this because one, and you'll find this at a lot of companies, not a lot of companies, I can't say. At some of the bigger tech companies I've worked at, there is no position called software architect. There's kind of developer/engineer, and then as you get more and more senior in that. So that's kind of where I'm at right now. I'm a staff engineer at my current company. So I kind of fit in, I think, what they would consider a software architect. But one of the things is that as you become a staff engineer, you actually want to remove yourself from the critical path of any given project, right? Which is, I think, where a lot of more junior engineers go wrong in their understanding of what a staff engineer does. You think a staff engineer is just someone who can crank out 10 times as much code as a junior engineer. But actually, staff engineers need to be figuring out ways you talk about the 10x engineer, right? And it's much in terms of scalability, right? You can be a 10x engineer instead of cranking out 10 times as much code as any other engineer by making 10 other engineers twice as effective. And so as a staff engineer, you want to be removing yourself from the critical path, not blocking on any specific project and waiting for your component to get done. But then the question becomes, well, then how do I still make sure I'm involved in the details and writing code? And I think these automated fitness functions are a great way to do that. Nathan, what are your thoughts on all of this?
Yeah, again, fantastic framing. One of the things I really liked is there's this idea of atomic versus holistic fitness functions, right? So this is that idea of like how granular do I drop in to the system, or how broad is my view of the system. And so I think, knowing that sometimes an atomic fitness function might be exactly that thing that you were talking about with like the arch unit of checking for the presence of cycles between components, right? That would be an atomic thing. It's a Boolean static code analysis step to make sure that we're hitting standards that we have. And it's just good hygiene, and we should do it. A holistic approach, right, would be some sort of like shared context, or some maybe larger combinatorial architecture aspect that looks at the system as a whole, and then you says, hey, are we meeting the standard? And if you put it in unit testing world, it's like maybe a unit test versus like an end-to-end or integration test, right? They're both important. They both give you different context and can help you understand. I also think that you're right. I know we've talked about this in a couple of podcasts now, that this idea that culture eats strategy for breakfast, right? I think it's been attributed to Peter Drucker, but who knows who it actually was set by. But the idea here is that, we'll always revert to the mean. All cultures revert to the mean. And so if the culture has this standard of using things like fitness functions to measure themselves, to constantly pry and prod, then when you revert to the mean, it's going to be the average use of that, right? If it's some hero who's swooping in and doing fitness functions when they're really desperate, but nobody else does it, the culture is going to revert to the mean of not doing these things. And again, it's not because it's lazy, it's because there's a set of expectations. When you get busy, things slip. And what slips is the definition of that culture, right? And so I think that's a really important piece here. And I think one of the reasons that they give an entire chapter to fitness functions in this book is that this is a way of setting the expectations of the behavior and saying, hey, look, we do all of these types of testing because we're testing the fitness of our application, of our infrastructure, of the way that the services behave. And all of us have to play a role, right? Architectures can guide this and set expectations, but yeah, everyone has to be involved, which is really, really, really cool insight.
Absolutely. And also just point out, I love what you bring up about culture eating strategy for breakfast, because we learned that from our book last week, Recoding America by Jennifer Polka, which was a little different from what we've usually done. Fun insider story on the podcast. We know that Recoding America is a little different from what we've done in the past, but we looked at our Spotify analytics and it got like 2 plays, which usually we get easily several hundred plays. And I was like, whoa, like I know this is a little different, but like, man, you guys really didn't like this. And then like a day later, Spotify was like, hey, we have a data delay. And then all the data came in, and surprise, surprise, we got about exactly as many plays as we usually get on our episodes. So that was good. I was texting Nathan. I was like, I'm pretty sure our entire audience didn't abandon us all of a sudden. But it would be kind of funny if they did. So glad to see that you guys still liked Recoding America. Well, I think this is a fairly good place to leave off. Oh, and I guess I should say before we leave off, but with Recoding America, I do like that as we've done this podcast, I think in every single episode, we usually wind up referencing a book that we've read in the past. And I'll just give a plug for any of our listeners to be well read, right? Maybe you won't read as much as we do. We understand that we have kind of an accelerated reading pace, but as you read all of these different books, it's really, really cool to see where they overlap and to be able to draw different wisdom from them and again, see the connections between them. So again, just if you're listening to this podcast, obviously, we're a big fan of reading. We're a big fan of engaging with deep, long form ideas. But I hope you see, as we discuss them, that these aren't things we just read and then talk about for 1 week and cast aside. We often are referencing things we've learned from these books over the course of multiple episodes. So hopefully you're seeing the value there. But we're going to take a quick break. We're going to be back a little more. Talk about fitness functions. We talked about the idea of evolutionary architecture. We're going to talk a bit more about automation and how you can use automation to build an evolutionary architecture. So we'll be back with that and more after a quick break. And we are back. Thanks for tuning in, listeners. Well, let's talk a bit about, like we talked about, automation. What are some of the seminal tools in the engineering toolbox to help us craft evolutionary architectures? Now, there's some you've heard of before, right? CI/CD, continuous integration, continuous deployment, right? You can do that through deployment pipelines, use feature flags, feature toggles. We've gotten some feedback from listeners, and we throw out some terms like this that they don't always know what we're talking about. So we'll take a bit to talk about some of these fundamental tools, right? So I don't know, Nathan, when you hear CI/CD, what do you think of when I say that?
Yeah. So, my career trajectory kind of happened, I got deep into cloud computing and really into the DevOps processes in the 2010s. And I saw firsthand this revolutionary change that took place where the rate upon which you could make incremental changes increased. And it did it in counterintuitively, the more frequently a team ships, the safer the output code is. If you're following these processes and procedures and you're putting up guardrails properly, you can do that high standard of testing and deploy cycle, that high rate of change, if you have all these tools in place, because the scary parts get automated, right? Like, I think if you look at companies had a very long release cycle, the change management was frightening because you're like, oh, well, what if I break everything? Or more importantly, the last 3 times we've made change management decisions, we have broken stuff, right? That this is why in like old school corporate enterprise software, more and more guardrails get put in place. And again, we're referring to the Recoding America book, but we see two trajectories. One where the bureaucracy gets so locked down that it takes forever to make even small changes, and then the Silicon Valley and tech world, in which they've come up with amazing engineering feats that allow us to have these evolving systems. And so 3 and 4 we kind of couple together, as what we're talking about here is that chapter 3 it talks about kind of the mechanics of engineering change management, and then in chapter 4 they get into like the philosophy, and that part gets really cool. But before we get into that, they say, yeah, look, here's why we have CI/CD. Here's our definition of incremental change, right? It's this like independently deployable unit that you can do, right? You can have some big complex thing, but you don't have to have some big monolithic deploy. And and this is actually where this philosophical debate of like, well, are we, is architecture this blueprint thing, or is it this thing where we're guiding the change management of a system? And yeah, like one of the things that was kind of funny is like anybody who's worked at like a big modern tech company, I think Carter is a good example of this, where he's worked at some really cool companies. Having like trunk-based development or feature flags or these other things that are kind of obvious no-brainer. Of course, we will, the whole idea of a feature flag and a feature toggle, which is like the original way that it was framed, I think, by the agile development community, was that a feature toggle allows you to decouple an artifact being released into your code base from the feature actually being turned on for the user. So by artifact, and again, we're getting a little into the vocabulary, an artifact is any sort of deliverable chunk of data, right? So a Docker container, or I should call it a container. Containers are artifacts. Packages published to NPM are artifacts, right? It's this unit of functionality that has some cadence upon which you can identify that piece. In more traditional software, when you do the release of that artifact, all the features in that artifact are just turned on, right? They're just part of it. And so there's risk in that every time I do a change management process, I update the software, I change the package, I do these things, I get the new features all or nothing, right? And so feature flags allow us to do something where we say, okay, we're going to toggle functionality A, like function A. And we can do this either at deploy time, like we just turn those on by default, or we use some independent system, like you've probably heard of tools like Launch Darkly or these other things where the business can decide to turn on a feature for everyone or A/B test with it. They can, see every other time somebody loads a page, the button changes size slightly, or they can do what's like much more sophisticated, which they call segmentation, which is I only want this feature to be released to a subset of my user base, right? This could be geographic release, like, oh, we're going to release this to US based IP addresses, right? Or we're going to let this only for people who've actually hit the checkbox that they want to alpha test features before everybody else, right? Like there's ways to segment things out. And again, they kind of show why these decisions and these changes to the way that DevOps works or the way that we build things has empowered these evolutionary architectures to take this.
Yeah, and like the rough mechanics of a feature flag is basically you have some database independent of the application that has a list, again, roughly of like, okay, button should be green. Is that set to true or false? And then your application will communicate with that database and then check the feature flag value and then enforce that behavior appropriately, right? And then obviously, like Nathan said, it can get more complicated. Do you want only alpha testers? Do you want only US based users? Things like that. But yeah, I mean, I love this because it does take some of the like high wire balancing acts out of the deployment, and you can just get the code out there and say, okay, the code is there, it's ready to go, but we're not actually going to turn it on until until we want to. And then if it starts causing a problem, we can shut it off immediately. When I worked at a large cloud provider, I built a feature which wound up needing UI changes, which was rare. Our team didn't do a ton of stuff that wound up needed to change the console version of the console implementation of our feature, right? Our product, I guess. Anyhow, and so I worked with the front end team to do that, and then as we deployed those UI changes, that's basically what it was. It was all hidden behind a feature flag. And so we had like 30 different regions we were scattered across. And we would do that. We would say, okay, we're enabling it for 40% of users in these 3 regions. And then we had all of our fitness functions, all of our monitoring, and we would monitor everything, make sure that everything was okay, and then say, okay, looking good, moving on. Let's up it to 100%, and we'll deploy it to 25% in the next 3 regions, right? And so that combination of tooling we had our fitness functions, which are enforced via monitoring and alerting. And then we had our feature flags, which allowed us to deploy or we were able to deploy all the code at once weeks before, and then just to enable it bit by bit. It led to a really safe release process, which was good because, again, at this cloud provider, like uptime and reliability was the name of the game. And so you really didn't want to do anything that brought the system down. So there were so many processes put in place to keep the system up. A lot of it was annoying, but some of it was really cool, like that. And so Nathan, you talked a bit about, so chapter 3 is a bit about that. And we should mention, we're going to cover through chapter 5 today. Chapter 3 was kind of those actual tools, feature flags, CI/CD, deployment pipelines, all that. Then we have kind of the philosophy of automating architectural governance. Lots of interesting stuff here. Anything that stood out to you?
Yeah, so chapter 4, which is titled Automating Architectural Governance, this is where they really start tying all these concepts together. This is also the final chapter of the first section of the book on mechanics. And you can see that they're transitioning into this more philosophical piece because they start talking about things like, let's see, there's like the coupling of systems, and they talk about this in fundamentals of software architecture of like afferent and efferent coupling. They go
very
into
different words.
Yes, one starts with an A and one starts with an E. But afferent coupling measures the number of incoming connections, and the efferent coupling measures the outgoing connections. If anybody's done graph theory, right, this is like sources and sinks, right? This is this whole idea of measuring incoming connections or outgoing connections in a directional graph. Um, there's a lot of talk on, well, how should systems be coupled? There's like this whole idea of like locality, like if it's close, things are close to each other, then there's more coupling that's acceptable versus things that are far apart, right? Services that have less to do with each other, parts of the system have less to do with each other should have fewer, coupling, or ideally zero coupling. And when we talk about release processes, or we talk about features, we talk about these things, right? This came up actually in conversation the other day, which is we're introducing it right now. Right now, folks, we are introducing a feature flag pattern to one of our divisions at the company I'm working for. And there's a huge training component. Like half of the work that we're working on is providing the backend for this feature flag system. The other half is building out examples, training, and changing the culture of how we approach feature flags. And of course, there's lots of terrible things you could do that deal with the coupling piece. For instance, some folks wanted a feature flag that also would trigger a database schema change as part of the feature flag being turned on. And of course, it was a good learning moment to being like, hey, this is dangerous because you lose the ability to roll back, right? Unless you have this ability to elegantly roll back by turning the feature flag off. Well, what's the latency on this? Is the system available, right? Like all these things that we've now coupled this data portion to the application behavior portion. And, so introducing this idea that, hey, can the application live in a world in which either schema could exist and intelligently handle this scenario where it detects that it's in one mode versus the other. And so therefore schema changes can happen independently, right? This is the architecture discussion, which is how do we safely change the system in a way that must be changed, but decouple certain aspects of the system. And I think early in the book, they actually talk about like, let's say you have like a rating system, and then you have like the advanced version of the rating system. Like, so it's full stars that you can do 1 through 5, and then maybe we start allowing half stars. Well, every system that consumes the star rating system, they might have some sort of coupling to whether half star is supported or not. And so therefore you need to be able to architect this change management where, okay, well, maybe these services continue to use the legacy star system, and these new things are using the fancy fractional star system. And then there's a transition path to safely move everybody to fractional stars, right? And this is that idea of this automating architectural governance, is that these are little puzzles to solve, right? It's not that it's insurmountable. It's not that there's a right or wrong way, right? They talk about, I think, in fundamentals is the least worst decision, right? Like that's an important concept here. And so, yeah, I would love to hear your insights here, because like there's a bunch of concepts that they bring up actually that overlap with the fundamentals book.
Absolutely.
That are really cool as they're applied to evolutionary architecture.
And again, folks, we can't say this enough. Read the book, right? We hope that you're getting a lot of good discussion or a lot of good insight out of these discussions, right? But at the end of the day, we are just breezing over some of these talking points. I will say with afferent and efferent coupling, it always reminds me. I lived in Brazil for a couple of years, and I'm roughly fluent in Portuguese. But the word for grandma and grandpa in Portuguese it's like avó and avó, or something like that. I can't even, it's just AVO with a different accent mark over the O. And I still don't know the difference. And that afferent and efferent coupling reminds me of that, where
Right.
they sound so similar. Again, the chapter 4 is titled Automating Architectural Governance, which I'm just such a huge believer in. And I think roughly any governance has to be automated. Trying to enforce it just by having a charismatic personality or being in everyone's business all the time. I think they talk about like the idea of scolding, and you don't want to be that as a software architect. So I think this is a fascinating kind of idea. Like, how do we automate architecture governance? One thing I really liked from this section was the idea of automated service discovery, which I know is can be standard in a lot of places, and I believe is standard in some of the places I've worked at, but I think it was kind of so abstracted away from me that I didn't appreciate it. But the idea with like automated service discovery is you have some sort of application, right? And that application, let's say it's like a microservice architecture. And so, like Nathan was talking about, like a star rating system. And so different parts of the application may need to communicate with that star rating system. Now, if you were just to do something like bare bones, it's like a personal project, maybe a school project, something like that, right? You would just know, okay, the star rating system is hosted at api.whatever.com/star rating or something like that. And you would kind of hard code that value in there. Service discovery tools, and I believe these are tools like Puppet and Chef. Instead, what happens is when a service is deployed with a pipeline, this is how they put it in the book. They say when a deployment pipeline deploys a service, it registers itself, location, and contract with a service discovery tool. When a service needs to find another service, it uses the discovery tool to learn the location and version suitability via the contract. So this is really neat because instead of directly communicating with the service, actually what you're doing is directly communicating with that service discovery tool, which then tells you the location of the service. So I love this because one, it's abstraction, which I'm a big fan of, right? We can change where that service is deployed without a problem because all we need to do is update its location within the service discovery tool. So if there's any need to switch up the deployment location, it won't affect the functionality of the other systems.
And this has changed a lot. I think you're right. There was a lot of like at deploy time, things changed. That's where Chef and Puppet would come in. Now in this Kubernetes world, internal DNS has become the service discovery tool, right? Kubernetes ends up giving us this you actually describe what's called a service. That's service is like a core primitive in Kubernetes. And the cool thing about the service registry in Kubernetes is that there's a convention. And again, this gets to that connaissance of naming, right? So this is one of those, and we'll get into this. This is something that comes up in, I think it's in chapter 5, but connaissance is this concept of how we measure the coupling of things. And connaissance of naming is a weak connaissance, a static weak connaissance, which is the ideal. If you're going to rely on some connection between two parts of a system, names are amazing because you don't have to know anything about the inner workings of it, right? And so if you put this in this idea of service discovery, if the domain naming service, DNS, is your coupling, saying, I don't know how it's running or where it's running, I just know here's the name of the rating system and maybe V1 or V2 or whatever, right? And then everything else is abstracted away. It's incredibly powerful. Right. And it used to be, I either kind of needed to know what data center it was in or what the IP address was or these other things. And now I just write my software in a way that I know if I ask the service discovery mechanism, how do I find you? It just responds with whatever simple answer it is. You get this incredibly powerful pattern where we can just build tools that expect to talk to other parts of the system that we have no control over. And that gives us a really cool thing. I think another piece that as far as like automating governance, some languages have this as a feature and many languages don't, which one of them is like cyclomatic complexity is something they call out, which is as an architect, you might want to set a constraint that says, we want this cyclomatic complexity to be a certain threshold. Like how often can things have cycles of referencing? There's some languages like Go, which actually forbid cyclic references. So you can only have what it would call a directed acyclic graph. Things always flow down to other states. And so there's no way that like package A can reference package B, which then references package A. That's forbidden. There are plenty of languages that do allow this. But the things like the compiler take forever because they have to think about all of the ways that this could violate certain race conditions and things like this. So this is like another good example where, again, we talk about the atomic versus holistic. The idea of service discovery, I'd say, is something that's holistic in that, hey, let's design this mechanism. We don't have to know anything about the implementation details. We just like find each other and we can test that. That's a holistic test that we can do. And then things like cyclomatic complexity. Well, yeah, we're doing static analysis. We're like, giving a score and seeing how much we might violate some principle that we've decided to put into place.
Well, programming languages are a great example of automated governance. Like you talk about with Go and how you have to, everything has to flow down. You can think about something like Python, which determines how you structure your code uh, because it's white space sensitive, which is why Python is an affront to God, because what language should care about your white space? That's my personal grief with Python. Um, so yeah, you can kind of, if you're thinking about automated architectural governance, you're familiar with this every single day. Any code you use has some form of automated architectural governance built into it. That's obviously at a more micro level, but you can imagine how that scales out to a more macro level. Nathan, is
Oh,
this a good time to jump
oh,
into?
I'll leave
Oh,
you. I'll leave it.
okay.
Leave the section. There's a Rob Pike quote. I just looked it up. It's so good, and it ties right into the Python thing. He shares your feelings about whitespace in Python. He says, "We have had an extensive experience tracking down build and test failures caused by cross-language builds, where a Python snippet embedded in another language, for instance, swig invocation, is subtly and invisibly broken by a change in the indentation of the surrounding code." Um, and so he's like,
Ridiculous.
yeah, this idea that white space can be the cause of bugs, like this, literally this invisible part of your code can cause bugs is really funny.
Defend yourself, Python lovers. Tell us why this is a good feature or language. Um, well, I think this is a good time to. Well, we'll take a quick break. Unless you have any final thoughts before we kind of jump into chapter 5, Nathan. All
No,
right. Well, we'll take a quick break, folks. We'll be back with chapter 5 and our closing thoughts on the books right after this break. And we are back. Thanks for tuning in, listeners. So we're going to round out our discussion with chapter 5. It's titled Evolutionary Architecture Topologies. There's lots of good stuff in this chapter. We're going to cover just some of the concepts here. But we're going to start with this idea of conessence, which is a measurement of coupling. The Melier Page Jones describes this as two components are conessent, but change in one would require the other to be modified in order to maintain the overall correctness of the system. Now, there are lots of different kinds of conessence. We're not going to go through all of them, but Nathan mentioned one earlier, like conessence of naming. You can imagine that we have a pattern where a certain type of component must always. Well, you can even just imagine. Let's say the code name of your system is Dalmatian or something like that, and so you have Dalmatian service, Dalmatian queue, Dalmatian processor, things like that. If all of a sudden we change the code name to be, I don't know, mattress. I'm just looking at the bed in my office, so forgive me for coming up with dumb names.
oh, Carter's got a place to take a nap in his office. That's great.
It's awesome. Yeah, it's tempting sometimes. I've had to develop some good self-discipline. Anyhow, but then now all of a sudden we're going to have to change the names of all of these systems. So these systems have what would be called conessence of naming, right? There's different kinds of conessence, like I wish I had everything in front of me, but I don't. But one of the kind of conessence, I don't remember what it's talked about, can be like almost like a conessence of structure. Like you might expect, like a data contract, right? You might expect if two components that they would need to have these types of variables to communicate with each other, right? And one of the points they make with conessence is that the closer two components are to each other within the system, it's more okay for the conessence to be a little stronger, right? So let's say we have two different objects that both need to be initialized with like a project ID and a project name and credentials or things like that, right? But they sit right next to each other in the system. They get used similarly. It's okay for them to be a little more consistent like that. But let's say that there is a completely separate system deployed across the company, but that in order to work with it, you have to provide the exact same attributes that you might need for a system all the way across the company, right? These two have been strongly coupled together despite the fact that they are very far apart from each other. And so that strong coupling makes for a brittle system, because now if I need to update some of those kind of initialization characteristics of one system, I need to update them in the separate system. And there's no way it might be hard to automate kind of that updating. And so again,
Yeah,
you create a tightly coupled brittle system.
Yeah, I think there's a graphic that we can't show you, through the podcast, but this is one of the few cases where the weaker something is, the better it is. So the worst connaissance is strong and dynamic. The best connaissance is weak and static. And so they actually show this continuum, and they actually show you there's this refactoring path. And I think this was actually brought up in the refactoring book as well, which is that we should always be moving towards the weakest and most static version of connaissance of the coupling between parts of a system. And again, naming being a great one. And think about this. You don't know anything about how Google.com functions at all, right? Our coupling to Google is that I can just type in google.com, or maybe it's even the default search engine in my browser. But the connaissance that I have with the naming of Google unlocks this ability for me to benefit from interacting with that system without having a single shred of understanding of how the system functions. The other end of that spectrum is like they talk about connaissance of timing, right? Which
This
is
would be
now
dynamic connaissance, right?
that's a dynamic connaissance. The coupling there is that, like, hey, the system functions if I intimately understand the timing of the interaction of several things.
Like
Right?
you must call this before you call this.
Right, and then maybe check until something has happened, and then I can do the next step. Right? We talk about how that gets really difficult to reason about, and imagine you do that times 100 things, where all of a sudden these things are coupled by the fact that they all rely on timing. And so that kind of connaissance is, and I think you can say connaissance or connaissance. I've heard both said, just by the way. So I don't think you'll sound stupid if you say
You'll at least sound as stupid as we do.
Right. I will say that little side note. I mispronounced idempotent for years. Like I said, like I am dipotent or something,
Oh.
and finally an engineering manager corrected me. And he's like, "What are you saying right now?"
Hey, I
And
had
I
a
was
friend
like,
who pronounced chaos as chose.
"Oh, okay." And that's the funny thing, right? When we're reading books or we're doing stuff on our own, sometimes you don't know what the pronunciation of something is. Luckily, we live in a time where it's much easier to find out. But for a long time, these little words will like live in your mind.
I saw
Rent
someone
free.
say once, if you hear someone mispronounce a word, it means that they've only ever read it, and that you shouldn't make fun of them, because like that's a really good thing to be.
Right.
It shows that in a lot of ways you're well read.
Right. Or if it also might show that you're sticking in the mud, like if you pronounce it GIF versus GIF. I'm like, oh, that's a contrarian right there. Like, love it. I love it. But yeah, so again, the idea here is like, connaissance is really cool. Actually, I think it's Jim Wyrish. He popularized the concept. He's like a prolific sort of legendary software architect that they reference in the book. They say there's a couple of rules around connaissance, such as the rule of degree: convert strong forms of connaissance into weaker forms. And then the other one is rule of locality, right? Which is, as the distance between software elements increases, use weaker forms of connaissance. And so these are good rules of thumb. And I think they warn you that if you are not careful about this, a couple of things happen. Number one, you get a big ball of mud on a distributed system, which is bad. That's like the worst kind of ball of mud. And then the second one is your system becomes very brittle to changes, right? If you have strong dynamic connaissance between all your parts, it becomes incredibly hard to reason about. You might have to jump into across 5 different teams and 50 different references, and the risk of you breaking something, right, is very high if it's deeply coupled.
This is such an anti-pattern I see out of either mediocre engineers or self-conscious engineers, or maybe just engineers who don't even know any better, is this idea that if I have to jump across 5 different teams and really dig into the depths of each individual code base, then I must be a really good engineer. Or if my code is complicated, only a complicated mind could come up with this kind of code, and so I must be a good engineer. And it's not true, folks. It's like John Osterhout says in A Philosophy of Software Design. If you have to read the code to understand it, then there is no abstraction. And abstraction is your best friend when writing software. Like Nathan talks about, we have a very loose coupling with Google. the entirety of Google is abstracted from us. And that's why Google is a bajillion-dollar company. You want to be writing good abstracted software. And the more tightly coupled all of your software is together, the stronger the forms of connescence between all of them. Like Nathan said, is going to be brittle to change. This actually kind of dovetails nicely into this idea of software reuse, which is interesting. This book takes what I think to many might be a contrarian stance, but I think amongst maybe the more enlightened of us is what the majority stance, which is basically how the book summarizes it. The more reusable code is, the less usable it is. Because if you try to make, listen, I get why people want to make reusable code. You think we write it once, we can reuse it, we'll save time, right? But the thing is, when you write that kind of reusable code, you form really, really, really tight coupling, and it makes your system brittle to change. What kind of reuse are we talking about here? This is where we get another fun story from that awful little startup I only worked at for a little bit, which was this idea that they said, okay, well, we have a customer object, right? And we know that customer object is going to be the same across all of the systems. So what we're going to do is we're going to create one customer package, right? We were writing in Node.js back then. So, we had like one customer class within the customer package or whatever, and we deployed that via npm. It would have been a dream if we had deployed it via some sort of internal npm registry. Instead, it was just you'd like download it via GitHub and rig it up to work in your machine. It was awful. Anyhow, and in that way, no one has to write the customer class ever again, right? The thing is, it's really easy to write the customer class, right? It's really easy just to write, having some wiki somewhere. Okay, these are the common customer attributes, and then I'll write my own implementation of it locally, just take what I need. It's really hard when you couple everyone tightly together like that. If I need to make an update to the customer class, it is a nightmare to get in, to update that. And now all of a sudden, because my systems are so tightly coupled together, you better hope that you didn't break the customer class, because if you broke the customer class, you broke everything else. And this gets into the idea of what they talk about, kind of an architectural quanta, which is the idea that a quantum is an individually deployable architectural unit. And so like a microservice is kind of the microservice architecture is kind of the idea to get as many different architectural quanta as you can, or as makes sense by the kind of bounded context you want it to represent. Anyhow, but then so we were like ostensibly a microservice organization, but because everyone had to rely on these common kind of architectural or these common classes, it actually wound up being basically a giant monolith. Like we were microservices in name only. And yeah, we were tightly coupled together, and all because of the software reuse. And so in this attempt to make reusable software, again, like to save time, we'd actually just created this big nightmare. I've seen this at several different places. I know, Nathan, you had said you'd seen things like this too.
Not only did I see it, I designed it, and it was. I mean, it's so embarrassing to talk about. We did this exact thing. We originally actually had a monolithic repo, which actually gives you this is a really nice way of when things are going to be coupled. If you did want to have this strong idea of like a customer class, you should at least, if you're in a monorepo, you can at least have it right up in your face, and you can deal with the fact that if I change the customer class, does the rest of the system build, right? Mm-hmm. If you're going to have that tight coupling, again, you're not violating locality. The locality of these things are together, and so therefore something like that is okay.
That idea, since these are closer together, it's okay for the connescence to be a little stronger.
And as an organization, you might say, I'm going to take the burden on of having an atomic description of customer. Where things get bad, and they talk about this, in fundamentals, but they also talk about this here. Service-oriented architecture is not microservices, right? We learned a lot from service-oriented architecture is actually where this terrible design pattern came about. And they talked about, oh yeah, there's this customer. So maybe I'll make a customer service. And so therefore everything has to talk to the customer service. And then then we never have to like redesign it. We'll make an SDK for it. And everybody will use the SDK plus the customer service. And then, yeah, all of a sudden you end up like having this really tightly coupled system that's dynamic, right? Because if I need to make a change to the customer service or the SDK for the customer service, I have to go then either allow 20 different implementations because I have to go and like wrangle every service that references customer service and like go be like, hey, please come use the new version. And you can run into weird issues. And so the idea is that, yeah, let's make a contract, right? And they bring this idea up. It's like, we're gonna make a contract of what it means to create a new customer or look up something about a customer. That'll be the loosely coupled piece, right? A lot of it's around naming, API endpoint stuff. That's the social contract that we've talked about in the past. That's how we can couple, like, hey, this is how we do interactions with this. But how you create the customer abstraction for your piece of code should not be managed monolithically. And so the issue that I had is that we had this like distributed pipeline and all these little lambdas in a step function that were doing a bunch of stuff. And we needed to define, let's say, some schemas and some data structures and a few other things. The funny thing was that each process really only cared about like maybe one or two components. And what we should have done is had a social contract and said, this is the description, this is the data that's expected, this is the contract. Instead, we created this is a terrible anti-pattern. We basically created a like shared library Python package that we would like up in an ivory tower work on, and then all of the lambdas were expected to consume the latest version of it. And then we would say they're compatible if all of them are using the latest version of the library. And they were all their own repos. And so then teams started managing different parts of the system, and you end up being like, oh, well, the right way of doing this is to update the library because then everyone has the thing. And then you realize that like you had to touch the code in 3 places to make one change into the staging environment, which is horrible. Don't do that. Like, stop, get some help, right? That's the great meme. And this is exactly why. Like all of a sudden, all the advantages of having decoupled microservices, you just created a monolith with one incredibly important dependency in the name of code reuse. Oh, well, we'll all do it the right way. You're like, it's actually terrible. Like, and I remember the engineers would groan. Like we went from this monolith to these like broken out pieces. And they'd be like, oh, I like there would be resistance to making a change in the system. Mm-hmm. And then you're like, I just failed, right? Like I did this the wrong way. This is not how we should have built this. And so, learn from my mistake. Don't do that. And if you're in the middle, hopefully we're catching somebody right now. You're at the very end of an FDR or an ADR or an RFC, and somebody's proposing this, and I hope that I stop you. I hope that I stop you right now, and that you delay your project by 2 weeks, and you do a little bit of copying and not dependencies between.
Learn from our mistakes. Mm-hmm. Recoding America actually mentioned this last week, and I think they even referenced this book. It's The Design of Everyday Things. I don't remember who wrote it, but I had to read this, at least sections from this book for one of my classes in the Georgia Tech Online program. Really fascinating. But one of the principles from it is this idea that there's no such thing as user error. If a user messed something up, it's because the system was designed improperly. Recoding America talks about it in the context of,
I love that.
Basically, pilots in World War II were crashing their planes accidentally because they were just hitting the wrong dials.
They looked identical.
They looked identical. And I don't know enough about flying. We should talk to Uncle Bob. He's a pilot. I don't know enough about flying to know exactly what they were messing up that was crashing the planes. But I've seen that pattern over and over again, where you build something and it get used the wrong way, and you see people say, if only the users would use it in the way it's supposed to be used, then they wouldn't break the thing. And I just think one of the best things you can do for yourself as an engineer is to really take on that mentality of there's no such thing as user error. If the user finds the experience frustrating or difficult, it's because you designed it the wrong way. And kind of like you were talking about, Nathan, with this really tightly coupled Lambda mess where you all had to use this Python SDK, right? I've seen people kind of retreat and say, well, if they would just have the most updated version, then this wouldn't be a problem. But I just, at the end of the day, I'm a huge believer that, like, to be a software engineer, you've already got to be a fairly smart individual, right? And if you work at the right companies, you mostly only work with really smart individuals. And so if those people are complaining about the way you built something, take a step back, listen to it. I think Brian Kernahan and Rob Pike mentioned it in The Practice of Programming, where they say, like, with pull requests, like if someone comments and says, hey, this seems a little off, just accept it. Or is it refactoring? They all blend together. But basically, yeah, if someone says this seems a little off, or I don't understand how this is done, like, that their impression, having just taken a first glance at it, is probably more correct than your impression kind of being deep in the weeds of it.
Yep.
Yeah.
So there's one area, I think one last topic I'd love to touch on.
Absolutely.
Which is, it seems like a contradiction, but it's also beautifully explained. So there's this concept of sidecars, and you may have heard this term.
Yeah.
This is actually another one that, you'll sound fancy at cocktail parties if you don't know what this is. So a sidecar, especially in the container world, it's literally a reference to those old motorcycles that had the little sidecar sitting on the side. This is where your passenger would sit, right? The sidecar is this idea of encapsulating some complexity in a standard way so that the business logic in a microservice doesn't have to deal with it. Okay, let's unwrap that a little bit. So let's say as an organization, you've decided structured logs is something that's really important to you, or shipping to a certain metrics and telemetry endpoint, or maybe you want some sort of circuit breaker or retry logic pattern. You can, there are amazing tools that allow you to add a sidecar that the application expects to be there. So for instance, let's say I want to use Datadog as my backend for observability data, but I don't really want to inject a bunch of Datadog logic into my code. You can use a little bit of there's a tool called OpenTelemetry, which allows you to kind of abstract things a little bit where you need to annotate. But the collector, how it gets shipped off, all of that stuff's taken out of your code entirely, and it's handled by a sidecar. And it literally is a container that runs right next to the container on the same box. So this is what's described as a pod, and you might attach some sidecars to your core logic. This sounds like all of a sudden we're contradicting ourselves. It sounds like we're saying, okay, every service should use this Datadog sidecar, or every service should use this observability and metrics thing. And it's true. You've decided to standardize and couple what the sidecar pattern is. But they actually talk about this. It's called orthogonal coupling. And they actually bring up mathematics. And they say when two lines are orthogonal, if they intersect at right angles, which also implies independence. In software architecture, two parts of an architecture may be orthogonally coupled, two distinct purposes that must still intersect to form a complete solution. The obvious example from the chapter concerns the operational concerns such as monitoring, which is necessary but independent from the domain behavior like catalog checkout. Recognizing orthogonal coupling allows architects to find intersection points that cause the least entanglement between concerns. And I think that's the part, right? Orthogonal coupling allows for certain design decisions to be made by, let's say, the DevOps team or somebody who's in charge of observability, so that they can have a single consistent way of looking at the world in a way that minimizes a ball of mud, right? We're not getting into everybody's code, forcing them to use a specific library. In the best systems, I actually can independently swap out the sidecars without the team who built the business logic even knowing, right? And so that's the thing, that's the decoupling that actually happens. That sure, physically on the machine, they're tightly coupled, but they're decoupled in the change management process. They're decoupled in the separation of concerns. And so I think it was a really good call out, because I've had the same question myself before. I'm like, wait a minute, am I tightly coupling the system if I decide to standardize on a log format or how we ship something to somewhere else? And again, this is like a good example of, hey, this is the least worst thing you could do. We've come up with a standard way. What's cool is software engineers aren't confused. They aren't like, oh, wait, on this project, I had to do it this crazy way. And this one, you're like, no, it's abstracted away. I don't have to worry about it. In the same way that you don't worry about, interrupts on your processor. It's like not something you think about, right? It's just like handled in the background by Linux, right?
Well, and you don't have to tell people, let's say your system goes down, or there's some sort of incident, and so then you have to dive through the logs, right? And let's say you didn't have the sidecar pattern, and instead you'd chosen a tighter form of like more brittle coupling, where you just had mandated a logging pattern and said, okay, make sure that when you log that you have the system name and the timestamp and what host it's running on and things like that, and we send all of that to cloud logs or something like that. Then the incident happens, the system goes down, you find out that this system had not implemented that specific logging format, and so you're lacking critical information to resolve the bug. Again, I think the wrong attitude is to think, if only they had, it was on the wiki right there. If only they had listened to me and had implemented the logging pattern that I had chosen. That's the wrong way of thinking about it, because you can't control that. You can't control and validate that every single engineer is going to implement the logging in the exact same way that you want. What you can do is do the sidecar pattern. And so you decouple a little. So there is still coupling. There's coupling on the host, like Nathan talked about, but you can you decouple the actual implementation. So engineers can just log the way that they want to log, and then you've designed this sidecar that consumes those logs, formats them in the proper way that you want to, and then logs them to kind of your central logging repository. And so it's just it's looser coupling. It's you don't have to reuse code again, like you could imagine, kind of saying, okay, everyone make sure that when you log, you got to use this Splunk logging library in this exact specific way. No. Let them log how they want to, and then you can create these sidecars that format everything in the way that you want. Really, really interesting stuff with sidecars, Conance. Like we said, we only scratched the surface. I hope you, as we've been discussing these things, you realize that why we've slowed the reading pace down just a little bit, just because this is half the book. We were going to cover this whole book in one episode, and I still feel like we have our show notes here, right? And we have covered maybe a third of the stuff that we wrote down. So we hope that you are still feeling that even if we slow down the reading pace a teeny tiny bit, that you're getting good technical discussion. And we hope we're doing the books justice. We really do feel, in a way, honored to be able to read these books by these experts in the field. It's just we hope that we're accurately conveying the information from the books to you, the listeners. I think Nathan, are we good to round out the episode and ask what we're going to do differently in our careers?
Let's round it out. This is a great segue into the end.
Absolutely. So we always like to say, what are we going to do differently in our careers as a result of this book? Nathan, what do you think?
Yeah. So fitness functions got its own chapter. I want to be more mindful that when I'm advocating for these different ways of measuring ourselves, we think of it as in sort of a totality of how does this serve the architecture, and how does this serve the evolutionary changes to the architecture, so that we can measure ourselves in a way that can respond to these changing conditions.
Yeah, I think that's similar for me too. Like I said, at the cloud provider I worked at, we actually did, I feel like fitness functions is something they did really, really well. It's something I've wanted to bring to my new company, and just be better about, like, it's something you can kind of leave by the wayside if you're not thinking about it strongly. So I want to do that. I also want to look more into like automated service discovery. I like what you brought up about Kubernetes and having that kind of internal DNS, and having that handle service discovery. That leads into like a larger thing. If there are two things I wish I knew more about and I don't, it's relational databases. I'm a SQL. I am an amateur at SQL. It's not my strength. And containerization is a big one. Just Docker and Kubernetes in general. I know them. I know the theory. I don't work with them as much as I would like. And so I was excited when you brought up that Kubernetes has this way of doing kind of automated service discovery. Because that's just, as a meta career goal, I would like to be better at those. I'm actually working with someone, a student, who's close to me, and they're trying to create some personal projects that just kind of stand out when they apply to internships. And so they're working on a little web app, and they're just running it locally, but they're going to host it on AWS eventually to kind of make themselves stand out. And I told them, like, when we do this, we'll do it together. we are going to deploy it using Docker and Kubernetes, which is total overkill for something like this. But I think it would be good for both of us actually just to get some experience
Well,
with what this looks like.
depending on how advanced you want to get, if you want to hear about what the cool kids are using, you'll hear terms like eBPF and Cilium, which is a way that you can do sidecars in a more efficient way.
Oh, cool.
And there's a really cool project called Istio, which is a service mesh. And that's a whole rabbit hole as well. If you think you like service discovery, take a look at service meshes. You can do really wild stuff that's all sidecar based. It uses this really cool technology called Envoy, which allows you to do really advanced routing with like no understanding in the business logic at all. Like MTLS is literally a Boolean value you turn on, and then all of a sudden all your stuff's encrypted between everything, and it's entirely abstracted away. So yeah, I think it's important to understand kind of like why these systems work, even if you're not going to stay in it day to day. This is great. It's a good reason to kind of like kick the tires and understand how these distributed systems function.
That's
so
part
well.
of why we slowed down the reading too, is because I was finding with a book like this, like I was actually going to ChatGPT quite a bit and saying like, what is automated service discovery again? Can you explain that to me? And again, I'll just give a plug for being well read. Obviously, how you advance and progress as an engineer or a software developer, whatever you want to call yourself, is by building things. You're not gonna you can't just become the world's greatest engineer by reading a bunch of books. But I have found, as we have read these books and as I've been working kind of my day to day, you start to see these concepts as the books talk about bubble up in actuality in the real implementation. And it's a really cool feeling when you start seeing that and start saying, I know the theory behind this.
Yep.
I know why we're doing it this way.
Yep.
I have found, even in just the 2 short months of doing the reading all these books, I feel like I'm really leveling up as an engineer. And so we hope that you feel like you are in a way leveling up too, just by listening to the podcast. But if you want to level up even more, read the book. And we can say who we would recommend this book to. Nathan, who would you recommend this book to?
Yeah, so I would put this is an advanced topics book. So
I'd agree.
This is definitely a book for somebody who's mid-career, probably. Like, this is the kind of decision making that you're going to probably start getting involved with. Who's also, you should really read Fundamentals of Software Architecture first. I think that some of this will repeat some of the concepts, kind of help drum it in. But it also gives you like a broad view where this is a very specific type of problem that you're trying to solve. I think, if I saw somebody who's struggling with some of these concepts, or if I thought that there was somebody who's now kind of in a new role in which they could influence the guide the evolution of the architecture, this book is a must read.
Yeah, this is great. I think kind of like Nathan said, I've worked at mostly like Silicon Valley kind of tech company, like kind of in that vein, right? And so reading through some of this, I'm a little like, oh yeah, I get it. I've seen a lot of this stuff play out in my career. But before I got into kind of these Silicon Valley tech companies, like I had no idea how these places operated. And you might kind of think to yourself that there's no way you can know either without actually going to work at them. So you can imagine someone who comes in as like an architect at a startup, and maybe you have experience where you've been at mostly like other startups or Fortune 500 places. Like this would be a great book to pick up and read, because this will give you a really great insight into how some of the more agile Silicon Valley places operate.
Yep.
I mean, I would recommend Fundamentals first.
Yep.
Because Fundamentals is a great book. That's one where I would even recommend Fundamentals to like a junior engineer who's really, really curious and wants to grow.
Yep.
Yeah. I even saw a really curious junior engineer who wants to grow. I would not recommend this book to them. I would say this is just a little too,
right.
It's a little more abstract.
Now, if you read Fundamentals, you're junior engineer, you read Fundamentals, and
yes.
This is the part of the book that like you got super excited about, I would say you're the exception, right? Do it.
Yes.
Do it at that point. Also, I will say, we haven't really talked about this, but the other reason I'd recommend this book is the authors are prolific in their field.
Yes.
Right. And it shows, right? This is not hot take medium posts where you're like, who is this person? Like, why are they having these
Yes.
opinions about stuff? These are people who've seen they work at ThoughtWorks and they've seen a lot of different patterns. They've seen what success and failure is. And it's very well founded insights that I think it'd be well worth your time.
The irony of this podcast is we've noticed that our interview episodes usually do better than our discussion episodes, which isn't a surprise, right? Obviously, getting to hear from the authors is very cool. But the grand irony is that if you want to hear from the authors, just pick up the book. That's where all of their thoughts are. It's really, really cool getting to, and again, we talk about this kind of long form ideas, right? But there's just a big difference between reading a random Medium post that takes you like 15 minutes to read by some nobody versus really engaging for weeks at a time with the ideas of Neil Ford and Rebecca Parsons and Patrick Qua and the person whose name I butcher, Pramod Sadalage. So all of that to say, if you're more junior, please check out Fundamentals, and really anyone, please check out Fundamentals first. But if you really liked Fundamentals, and if you're whereas Fundamentals gives you an overview of kind of all of the different common software architectures, this is more about the theory and practice of evolving a software architecture. This book is for you. Who knows? Maybe we'll change our recommendations next week when we cover the rest of the book. But we hope you enjoyed this episode. We hope that, again, you find that we are still able to do deep technical discussion, even if the reading pace is slightly different from what we've been doing in the past. Please let us know. You can find us at Book Overflow Pod on Twitter. That's where we are on YouTube as well. Please leave a comment on YouTube. That's a great way to get in contact with us, or tweet at us. That's a great way to get in contact with us too. For some reason, Spotify lets you leave comments now, and we saw that one person did. So you are seen and heard, person who left a Spotify comment.
Wow.
Yeah, look at you. You are a pioneer in this industry, leaving comments on Spotify podcasts. And always contact at bookoverflow.io. That's a great way to reach out to us too. Thanks for tuning in, and you have a great rest of your day.